On October 9, an ISS experiment has been performed in collaboration with the European Space Agency and the Delft University of Technology. The goal of the experiment was to test new artificial intelligence algorithms on a flying robot in space. We focus on automatically learning algorithms. In this case, the robot is learning to see distance with only one eye. Usage of learning algorithms in space is rare, because they're deemed unreliable due to their inherent unpredictable outcome. Several years ago, NASA and MIT developed and launched a platform called Spheres to the International Space Station that enables scientists to test their algorithms in a safe manner. Using this platform with a recent stereo vision upgrade, called Vertigo, our experiment was able to autonomously explore part of the ISS, while at the same time learning to navigate with only one camera. In order to prepare for the experiment in space, several steps have been taken, of which most noticeable are the quad-rotor experiments done back on Earth. Using a small and cheap commercially available quad-rotor, called the AR Drone 2, we were able to test our behavioral algorithms first on Earth. This drone has been upgraded with an extremely lightweight stereo camera, which was developed by the MAV lab in Delft 1 year ago. The weight of this camera is equal to less than only one sheet of paper. Here we see some actual footage from this camera during our experiments on Earth. Note that the colored image to the right is called the disparity map. This contains the distances calculated from the difference between the left and right camera. A bluish color means far away, lighter or red colors denote close by. In the quad-rotor experiment, the drone had to autonomously explore its environment. In the beginning it would primarily use the distance information calculated from the stereo cam to do so. By means of a sophisticated algorithm based on the self-supervised learning method, the drone would simultaneously learn to see the same distances using only one of its cameras. After a learning period, the drone temporarily switched off one of its cameras and continues exploring with similar performance as when using stereo vision. Having proved the viability of the method on the drone, the next step was to apply this research in space. As mentioned earlier, robots in space never before used machine learning in their control in fear of unforeseen circumstances with catastrophic results. However, the learning method used in this project was specifically designed to handle this concern head-on. The robot is evaluating the certainty of the learned results in real time, simply by comparing them to the reliable stereo vision system. Therefore, both robot and researchers can be confident the robot will behave within expected parameters. Of course, several fundamental differences between the Earth and space experiments had to be bridged. For one, the robot in space can freely move in all directions, while the quad-rotor is in some ways limited by gravity. Secondly, training data that can be used beforehand was not available for the ISS, but this is where the self-supervised learning comes in best. Thirdly, hardware differences between the Spheres satellites and the quad-rotor are significant, but fortunately in favor of the space experiment. Due to the absent requirement of weight, images from the Spheres stereo camera are of much higher quality than those of the quad-rotor. Also, the computer in the Spheres robot is slightly faster. The Space Systems Laboratory at MIT has kindly provided access to their testing facilities, such that the experiment could be tested as much as possible on Earth. For instance, a frictionless table was used to validate the algorithms previously running on the quad-rotor. The experiment in the ISS was performed under supervision of astronaut Kimmya Hui. In the first part of the experiment, Kimmya manually moved the satellite through the Japanese experiment module in order to collect limited amount of data. This was meant as a contingency in case of complete failure of the algorithms, in which case some data of the surroundings in the ISS are captured for offline analysis. After successful completion of this part, the satellite autonomously flew through the module itself. The robot was able to explore the ISS only using its stereo system. In addition, during the flight, the robot was able to learn how to estimate monocular distances with just one camera. Unfortunately, before the robot could use the monocular distances, a system error occurred in the satellite, stranding the test. The experiment is still designated a big success as the primary mission of data gathering and learning was fulfilled. The reason of the unexpected problem is being investigated by the MIT Spheres team, but it is already shown that the error lies outside of our new AI code. Based on the gathered data and preliminary results, we expect a follow-up experiment to show fully learned monocular control in space.